Hello and welcome to this video presentation for my final project for my module AI for Earth Observation at University College London. The aim of this project is to investigate how machine learning can be used with satellite Earth observation data to characterise flooding. More specifically, we're looking at two questions. First, can machine learning identify the spatial extent of flooding? Essentially, where is water present? And second, can we go beyond flood extent and estimate something more physically meaningful? Flood depth. To answer these questions, I developed a 3-notebook workflow that combines Sentinel-1 radar data, Sentinel-2 optical imagery, terrain information, and several machine learning approaches. Before discussing the models, it's important to understand the real-world event being studied. The main study area is Fish Lake in South Yorkshire, a village which experienced severe flooding during the November 2019 River Don flood event. Following intense rainfall from storms Kira and Dennis, water levels rose dramatically, causing widespread flooding across the floodplain. The River Don at Fish Lake reached a record peak level of approximately 6.87 metres, and the event resulted in major disruption, evacuations, and emergency response operations. To test whether machine learning models actually learn general flood behaviour rather than just memorising one image, I designed the experiment around 3 satellite scenes. The first is Fish Lake, November 2019. This is the main training scene where the models learn flood patterns. The second is Bentley and Tolbar, November 2019. This happened during the same flood event, but in a different location nearby. This allows us to test spatial transfer. Can a model trained in Fish Lake work somewhere else? The third is Fish Lake, January 2021. This is the same location, but a different flood event caused by Storm Christoph 14 months later. This tests temporal transfer, whether the model works months later under different conditions. To detect flooding, the main data source is Sentinel-1 synthetic aperture radar, or SAR from Sentinel-1. The advantage of SAR is that it works independently of sunlight and can collect data through cloud cover, which is extremely important during storms. The physical principle is that smooth water surfaces behave differently from normal land. A rough surface, such as vegetation or soil, scatters radar energy back towards the satellite. However, calm water creates specular reflection, meaning the radar signal reflects away from the sensor. As a result, flooded areas often appear much darker in SAR imagery. In this project, we use both VV and VH polarization. VV means transmit vertical, receive vertical, and VH means transmit vertical, receive horizontal. Different polarizations interact differently with vegetation and surface roughness. VV is sensitive to surface changes, while VH provides additional information about more complex land cover, such as flooded vegetation. These radar features are combined with terrain information to create the inputs for the machine learning models. While Fish Lake is very small, I wanted to put something in this video specifically related to the village. So, supposedly in Fish Lake, there is a local legend that a mythical beast called the Cockatrice of Church Street lives by the churchyard in the village, and if you hear it, you'll never sleep again. The cockatrice is a kind of dragon or serpent with a rooster's head for reference. I thought a good way to keep you awake watching this video is if occasionally the cockatrice pops into the video and gives us some top tips about things about this project and its code. Now let's move into the coding workflow. We're currently on Notebook 1, which focuses on preparing the satellite data and creating a baseline flood map. The first step is connecting Python with Google Earth Engine. Google Earth Engine allows us to access and process large satellite datasets without manually downloading individual images. The Cockatrice says you should sort Earth Engine access before you do anything else. You can't get access to the data required for Notebook 1 or either of the following notebooks without it. Start by registering for a project to get the project ID. Here we initialize the Earth Engine environment and import the required libraries. These are Python's EE and GEE map libraries. GEE allows us to execute complex geospatial queries directly in Google Colab, avoiding large TAL downloads. We authenticate our pipeline using a dedicated Google Cloud project ID here, and make sure to allow access to your Google credentials. The notebook then loads the 3 Sentinel-1 scenes and extracts the required bands. For each scene, we calculate changes between pre-flood and flood conditions. The idea is quite simple. If a pixel becomes significantly darker in SAR imagery, this could indicate flooding. We combine 2 conditions, a low flood period VV backscatter value and a strong reduction compared with the pre-flood image. This creates a threshold-based flood mask. This threshold map is important because it gives us an initial flood estimate. However, this is only a rule-based approach. As we move on to Notebook 2, we explore whether machine learning can learn a better and more general flood classification than this general rule. Now we move on to Notebook 2. Notebook 2 is where the machine learning experiments begin. First, we build a feature stack for every pixel. Each pixel is represented using 9 variables: pre-flood VV and VH, mid-flood VV and VH, changes between dates, VV-VH ratio, elevation, and slope. This transforms the satellite image into a dataset where each pixel becomes a machine learning example. One challenge is that the threshold map itself is not perfect. Instead of training directly on every pixel, we use a semi-supervised approach. We divide the pixels into 2 groups: a confident core, pixels where the flood signal is very clear, and an ambiguous margin, pixels where the classification is uncertain. The models only train on the confident pixels, then we test whether they can resolve the difficult cases themselves. The Cockatrice says you should read the confident core/ambiguous margin split before judging Notebook 2's results in the classification. Without understanding why the training scene gets split that way, the IOU numbers being evaluated on specific pixel subsets, rather than the whole scene, will look random. We compare 3 different machine learning approaches. First, random forest. This is a tree-based model that is good at learning complex relationships between multiple variables. Second, support vector machine. This finds decision boundaries between flooded and non-flooded areas, or another way of putting that is it establishes structural hyperplane boundaries. Third, a convolutional neural network. Unlike the other models, the CNN also considers spatial context by looking at a 3x3 pixel neighbourhood around each location. Generalization, as well as accuracy, is important in this notebook. The models are tested on the original Fish Lake scene, Bentley and Toll Bar, and Fish Lake in 2021. This allows us to see whether the model learned a general flood signal. Interestingly, the CNN's performance dropped more on the temporal scene than on the spatial test scene. This pattern indicates that the CNN could have learned acquisition-specific patterns unique to November 2019, rather than a universally transferable flood signature. The main result is that the random forest was the most consistent model across locations and dates, suggesting that it captured relationships that transferred better than the more complex CNN approach. Finally, we move on to the final notebook, Notebook 3. After identifying flood extent, the final challenge is estimating flood depth. This is much harder because satellite imagery does not directly measure water depth. Due to this, we create a depth proxy based on terrain called height above nearest dry pixel, or HAND. The idea is, how much higher is each flooded pixel compared to the nearest dry pixel? This provides an approximate representation of how water may accumulate across the landscape. We then compare 3 regression approaches using a Gaussian process regression with an automatic relevance determination kernel to model depth. The first uses SAR plus terrain information. The second uses Sentinel-2 optical information, including water indices such as NDWI and MNDWI, or modified NDWI. The third combines both sensors. The Cockatrice says that you should be aware that sensors may be asynchronous. While SAR here captures the peak of the flood through cloud cover, cloud-free optical imagery for Sentinel-2 can usually only be captured some days later during a recession phase. This temporal offset may be unavoidable sometimes. The results show that combining multiple sensors performs best. However, the overall prediction strength is limited. This is expected because this area of South Yorkshire is a very flat floodplain, and the depth proxy itself contains uncertainty. The model is better at identifying relative differences rather than producing exact water depth measurements. The Cockatrice says that you shouldn't be alarmed by the low R² in the depth regression. As the floodplain is so flat relative to the depth proxy's resolution, this is expected, but the result that matters is the relative improvement from combining SAR and optical features, not just the absolute R². To understand why the models make their predictions, we also apply explainable AI methods, including this ARD length scale comparison. SHAP values, or Shapley additive explanations, on a random forest regressor show which features contribute most to predictions. This helps us to discover why each model made predictions the way they did. Finally, we monitor computational cost using CodeCarbon. Because much of the data processing was performed through Google Earth Engine, the local machine learning workflow remained relatively lightweight, even though, as you can see, the code has been run many times. To conclude, this project demonstrates a complete Earth observation machine learning pipeline for flooding in South Yorkshire. First, satellite data is processed to detect flood signals. Second, machine learning models are trained and tested across different locations and events, looking at flood extent. Third, multi-sensor regression is used to investigate flood depth estimation. The key finding is that combining different Earth observation sources improves flood characterization, but testing model transferability is essential before applying AI methods in real disaster response situations. Thank you for watching.